Hello everybody. For today's video, I'll be sharing with you a little bit about the OSENSA FTX-300 LUX Plus transmitter. Before we begin, you should know that this is a 3-channel transmitter, but for this video, I'll only be looking at 2 channels. Also, to offer a little insight, this product is ideally suited for MRI research applications because of its incredible accuracy as a fiber optic temperature sensor. So, the first thing that we're doing here is we're opening up OsensaView. We want to communicate with the device, so we're going to select the COM port, and the baud rate by default is 9600 for this USB. That's all good, then we can hit connect. I like to go to digital view right away to make sure it's connected, and I know my Modbus ID is 247, so I'll just select the first 2 channels and click start. As you can see, it's connected and both channels are reading temperature. Right now, the standard deviation right here and the mean are being calculated over a 10-second window, but if I right-click and hit display settings, I can change the window size. So, let's say you wanted to calculate the standard deviation over 30 seconds, for instance. You would just increase this number here to 30, but I like to leave it at 10, so I'm not going to do that. You can also turn on all the rest of these options or whatever you want to do, but I'm just going to leave the ones I have on already and hit accept. So another thing we can do is increase the sampling speed. Right now we're set at 500 milliseconds, so that's how often it's going to update this reading. But because it's so low noise, you can barely even see that these numbers are changing, which kind of gives it the appearance that they're changing every few seconds, even though they're not. So because of this, I'm going to select something that updates with every reading, which is the light level. So every time this light level changes, you can see that it's actually updating a reading. Now we can dial this number down and get this light level updating much quicker, like 180 milliseconds, or actually we can go really low, even all the way down to, let's say, 30 milliseconds if we want. And now you can see on this USB cable, the light will be blinking way faster now because it's reading and writing that quickly. The thing is, this isn't even the fastest we can go because our communication is actually being limited by the baud rate right now, which is set at 9600. So I'm going to stop this and change the device to communicate faster. So to do that, I'm going to go back to config and click RS45 baud rate because we're communicating over RS45 at the bottom of the unit. And then I'm going to click read just to make sure I'm reading at 9600. And then I'm going to change that to 115/200 and I'm going to click write. Okay, then a little warning pops up and I can ignore that. And then it asks me for a password, which is by default 0. After a moment, this message pops up saying, write successful. Would you like to reconnect with a new baud rate? Yes, I do. So now if I click read, it's showing that we're reading over 115/200. And now that will allow us to read at the fastest rate possible. So if I go ahead over here and I click start, now you can hardly even see how fast these numbers are updating. On top of that, if you look over here at the temperature, you can see how stable our readings are. Basically, we've got these 2 probes in a textbook, which acts as a big heat sink so that their temperatures remain very similar. And we can see how similar the temperatures are down to 0.01 degree precision. We can also look at the standard deviation, which is a measure of how much noise there is on the readings. And if we look at that, we can see that the standard deviation of noise on our probes is down at about 0.004 degrees. So that's to the 1,000th of a degree. And that's how accurate our system is. Our program also shows a max and a min temp and the change in temp. So we can see over the last 10 seconds, the most it's changed temperature is about 0.02 degrees. And this is just 10 times more accurate than any other system out there on the market. I mean, you're just not going to find anything else like it. We've also got LED current this is how much current the LED is driven at, and it can go up to 4,000. So we have a ton of headroom here. We can also look at this even better if we go to the graph and record view. And as you can see, I've already begun to set this up. So we're going to graph and record axis 1, channel A, as well as axis 1, channel B. We also have the option to change the sampling interval here too, and everything's adjustable on the go. So I'm just going to go ahead and click Start Graph 1. You can see this window is in auto scale mode. So right now it's going from 24.18 degrees to 24.22 degrees, which is just 100th of a degree resolution here. So let's change the scale and manually scale it to a more reasonable number, like let's say 23 to 25 degrees. So now we can actually see how flat our graph is, and even better, let's make it 24 to 25 degrees. Okay, now we have 1 degree full scale on the graph, and we can easily see how flat our temperature readings are. There's basically zero noise in them. Now, this is impressive because all the competitor systems on the market can show 1 decimal place precision at the most, and they'll still be noisy at that. Whereas we're at 2 decimal places, and we can see almost no noise. Now, it's updating every half a second because that's what we have set up over here, but we can dial that right down again all the way to 30 milliseconds. So here we are. We're going pretty quickly here. You can see the light levels numbers changing pretty quickly. I can actually, here, let me stop this one because it's trying to communicate to both of these, and that's probably slowing it down a bit. So overall, this is how stable and flat the temperature is when the probes are held in a book. But let's say we take out one of these probes, such as the PRB-400 for instance. It's got a 400 micron glass fiber, and I've got a mug of cold water here and a mug of warm water. And I'm going to just change this graph back to auto scale mode so we can see everything as it changes as I dip this probe into the cold water. Now it's around 0 degrees C, and if I put it next to an ice cube, you can see on the graph it gets down to about 0.2 degrees C. Now let me take it out and put it in the warm water, and you can see here we've got a nice smooth graph that's shooting up to about 40 degrees. This is how fast you're going to see temperature respond, going from hot to cold with super smooth graphs. Over here you can see our mean. You can see it's quite big right now, and the standard deviation is huge because it's going to take 10 seconds to update. So once that 10-second window is up, you'll see these numbers drop and they'll become much smaller. Well, actually I'm saying 10 seconds, but I think it's at the 60 seconds right now. Yeah, so that's why it's taking so long. So let me change that to 10 seconds. And now our standard deviation is much lower, and it'll continue to get even lower. This is excellent when you're doing medical type of temperature sensing and you need super high precision. Say, for example, you're running it in an MRI machine and you want to see what happens when you turn on the MRI and start heating up a patient or an implantable device or something. This will give you the precision that you want down to 100th of a degree. No other system on the market does that. In fact, most of our competitor systems use a technology called gallium arsenide, and as soon as you turn on the MRI machine, the electromagnetic fields shift the temperature reading. And, well, on a 7 Tesla machine, you'll see a shift of about 3 degrees as soon as you turn on the machine, which totally screws up your accuracy, and you won't even know what you're reading anymore because it'll be off by 2.5, 3 degrees something like that. At a 1.5 Tesla MRI, the shift is less, but it's still, a couple tenths of a degree. And why would you want to worry about that when this system is perfectly accurate and won't shift when you turn on the machine? Anyway, that's the PRB-400 probe. It's the premier probe we sell at the moment for MRI and research applications. I think that's all I wanted to say. Anyways, let's just throw that back in our textbook. Just give me a second here to wipe this off. Now let's take a look at the PRB-100 probe. It's a slight larger diameter. It's going to react a little bit slower. Here you can see in the graph, as I put it in the cold water, it takes a little bit longer to react and get right down to near 0 degrees. Now if I put it in the warm water, it shoots up and slowly gets to 40 degrees. The nice thing about this probe is it's made from plastic optical fiber. So if I take a hammer here and hit the probe against the table, you basically can't break it. Like I can bend it, I can whack it, I can drive over it with a car if I wanted to. I can do whatever to it, and it's seemingly unbreakable. A lot of customers like the durability of this style of probe, this plastic optical fiber probe. You can't break it, and that's another thing that's unique to our product. All of our competitors use glass fiber, which is very fragile. The last thing that's very compelling about this software that no one else offers, besides all of these statistics and stuff, is that you can right-click on the graph and you can do a differential measurement. So you can pick a value and subtract your reading from the reference value, which can be useful for some experiments. Another thing that you can do is you can pick what parameters you want to graph, and you've got two axes. You actually have an axis on the left-hand side, and you can turn on an axis on the right-hand side. For instance, right now we're just graphing temperature, but on the right-hand side we could also graph LED current if we wanted to. And the way we do that is we come back to our graph window and we stop the graph. Then I'm going to enable two more channels that are going to be on axis 2. They're still going to be on channel A, but I'm going to be graphing them on axis 2 now. So if we start the graph, we've now got LED current on axis 2. We've got temperature on axis 1. And if I right click and hit data selection, I could choose to switch and graph decay time or PCB temperature, and I could compare it to anything. Like I could choose average temperature or whatever I want, and all of these things are able to update live. So if I just mark these things here, you'll be able to see them show up on the graph right away. It all updates super fast. But I'm just going to go set it back to temperature and LED current because those are the most important. Now, the final thing I wanted to show you is this calibration table editor. So you can actually create your own calibrations, and you can fine-tune your calibrations if you want. So just to give you an idea of what it looks like, we'll click on the table editor and we'll ready channel A. Password again is 0. So this is what a calibration table looks like. We've got temperatures ranging from 100 degrees down to minus 40 degrees every 10 degrees. And we have a time decay value. So the time decay value is what this fluorescent material at the end of the probe is doing. The electronics are reading how long this fluorescent material is glowing for, and that's what your time decay value is. Your time decay value corresponds to temperature with this lookup table. So using this software, you can very easily calibrate your own probe, add more points, extend your temperature range, or really zoom in if maybe you want to do a calibration every 1 degree. And that's all possible if you just edit this table, write it back into that channel, and there's 3 different channels that you can write into. Overall, this program is very flexible. It's got a lot of features. You can also set up some passwords and change them at any time if you want to do that. There's a few other preference folders you can change or save, such as configuration files, calibration tables, data tables, or data files. You can play around with all of that. And yeah, I think that covers everything. Hopefully this demonstrates well the capabilities of this program. And thanks for watching.